Hello and welcome back to my channel. This is Walter here, and today I'm going to be taking you through the Further Pure Mathematics paper. That's paper 11 for October-November 2020. So let's get started. Question number 1. The matrix M is given by M is equal to 1B01 multiplying A001, where A and B are positive constants. So on A, the matrix M represents a sequence of two geometrical transformations. State the type of each transformation and make clear the order in which they are applied. Now you need to understand that for a composite transformation, it is found by multiplying the matrices in reverse order, which means here that the second matrix here, A001, is the first transformation, followed by the first one. So let us start with the matrix A001. Now for A001, we can consider a unit square on the Cartesian plane. For the unit square, this point is the point 10, and this point here is the point 01. Now the point 10 is being transformed to the point A0. So the point A0 could be perhaps here. And the point 01 is being transformed onto the point, in this case, again 01, which shows us that the y-axis is invariant. So we can conclude here that the unit square is being transformed parallel to the x-axis by a stretch of vector A. So that's the first transformation. So we're saying it's a stretch parallel to x-axis with the y-axis invariant. Let us now consider the first matrix. For the first matrix, we have the unit square, and we will transform the point 10 first. So for the point 10, it's giving us an image from the matrix of 10. And this shows us that the x-axis is invariant. Again, we will transform the point 01, and the point 01 in this case is given as an image of B1. Now the point B1 can be, say, here. And again, you can notice that this is showing that the unit matrix is being sheared parallel to the x-axis by vector B. So this second matrix is actually a shear parallel to x-axis, with the x-axis itself being invariant. So these are the two transformations, and it's in this order. First one is a stretch, and second one is a shear. So these are the two transformations as required by part A. And let's move on to part B. It goes the unit square in the xy plane is transformed by M onto parallelogram or PQR. So what they're saying here is the unit square is being transformed onto the parallelogram. So on B they say find in terms of A and B the matrix which transforms the parallelogram or PQR onto the unit square. So we're looking for a transformation that takes the parallelogram back to the unit square. Alright, so the matrix M for the transformation is here. M is equal to 1B01 and A001. So this is the transformation that's taking the unit square onto the parallelogram or PQR. Let's simplify this. So that's 1 times A plus B times 0. So this gives us A. 1 times 0 plus B times 1. That's B. 0 times A plus 1 times 0. That's 0. And 0 times 0 plus 1 times 1, we get 1. So we have here the matrix M. And in order for us to get the matrix, which takes the image, the parallelogram, back to the unit square, it means we would need to find the inverse of M. So let's start with the determinant of M. And for the determinant of M, that's A times 1 minus B times 0. So A times 1 is A and B times 0 is 0. So we get A as the determinant. So if the determinant is A, then the inverse now will be saying 1 over A. And we switch positions for A and 1. So that's 1 here and A. And the signs for B and 0. So that would be minus B here and 0. So we now have the inverse, and that's the matrix that transforms the parallelogram back to the unit square. So that's our answer right here for part B. Let's move on to part C. It is given that the area of OPQR is 2 square centimeters and that the line x plus 3y is equal to 0 is invariant under the transformation represented by M. So find the values of A and B. So we have two important things here, and let us start with the fact that the area of OPQR is 2 square centimeters. Now OPQR, remember from the previous question, OPQR is the parallelogram which was transformed from the unit square by matrix M. Now we know that if we multiply the determinant of the transforming matrix times the area of the object, which in this case is the unit square, which has an area of 1, we should get the area of the image, in this case, which is the parallelogram, that's 2. Now we've gotten the determinant of matrix M to be A, so A times 1 is equal to 2. So we can therefore say A is equal to 2. So we now have the value of A. Now let us go on to the point which says that the line is invariant under the transformation M. Now if the line x plus 3y is invariant, we can transform any point on this line and we should get the same point coming out as the image. So let us consider and say for x plus 3y is equal to 0, we can make y the subject and we get y coming out as minus a third x, which means that the general point on this line when x is equal to k is, in this case, that will be k and minus a third k. So we're just saying here, we just want a representation of any point on the line. And we say when x is equal to k, what is y? Y comes out as minus a third k. So k and minus a third k represents any point on the line x plus 3y is equal to 0. So if the line is invariant under transformation M, it means that if we multiply the matrix M times any point on the line represented by k and minus a third k, we should get the output coming out the same since it's invariant. Now the matrix M, we have already found it to be AB01. That's AB01. So we're going to multiply it by k and minus a third k, and we would expect the result to come out the same since it's invariant. So let's multiply here. So we have a times k, which is ak, and b times minus a third k, so that's minus a third bk. And we also have 0 times k, that's 0, and 1 times minus a third k, that gives us minus a third k here, and it's all equal to k of minus a third k. And right now we can equate top elements, so that would be ak minus a third bk is equal to k. And if we can divide by k for all the terms, we just get a minus a third b is equal to 1. But we've gotten a to be 2, so we can say a is 2, so that's 2 minus a third b is equal to 1, since a is 2. And we can now work out for b. Okay, so subtracting, so we're getting minus a third b is equal to minus 1, and therefore we get b coming out as 3, solving this. So we now have the value of b coming out as 3. So we have our two answers. A came out as 2 and b came out as 3. So these are the two solutions here for this question. And that's how we do it. So let us now move to the next question. That's question number 2. Question number 2. Use standard results from the list of formula MF19 to show that the summation from r is equal to 1 to n of the form 7r plus 1 bracket 7r plus 8 is equal to an cubed plus bn squared plus cn, where a, b, and c are constants to be determined. So here we're supposed to use the standard results, and this here is the set of standard results that we are expected to use. So you can find these from the list of formula. So in our question here, we have the summation from r is equal to 1 of 7r plus 1 bracket 7r plus 8. So I'm going to express this with these two brackets expanded. So that is going to be the summation from r is equal to 1 up to n. And if I expand the brackets here, I'll get 7r times 7r, which is 49r squared. And 1 times 7r plus 7r times 8, this is going to give us 63r. And 1 times 8 is 8. Now you need to know that the summation is distributive. So this means that this can be equal to the summation from r is equal to 1 of 49r squared up to n, and that's plus the summation from r is equal to 1 to n of 63r, plus the summation from r is equal to 1 all the way up to n of 8. So this is what we have right now. So we can actually apply the standard results. Like for the first one here, we have the summation with the constant 49 here, which can be factored out, of the form r squared, which means we can work with this second standard result. So that means that this will translate to 49 of the summation of r squared, which is a 6th n of n plus 1 bracket 2n plus 1. I'll also go to the second one, where we have the summation from r equals to 1 to n of 63r, and I'll factor out 63. And for the summation of the form r, I'll use the first standard result here, which is half of n plus 1, like this. And lastly, for the summation from r is equal to 1 to n, this just gives us 8n. So all we now need to do is simplify. So this is going to give us 49 over 6 of n. And here I'll expand these two brackets. So that'll be 2n squared plus 3n plus 1. And that will be plus, here I'll be having 63 over 2n of n plus 1. and that's plus 8n. Okay, so now we can say 49 over 6n times 2n squared. This is going to give us 49 over 3n cubed. And then 49 over 6n times 3n, this will give us 49 over 2n squared. And 49 over 6n times 1, that will just be 49 over 6 of n. And that's plus 63 over 2n times n, that's 63 over 2n squared. And 63n over 2 times 1, that will be 63 over 2n, and that's plus 8n. Now let us simplify. So grouping the like terms, we'll be having 49 over 3n cubed, and here we have the terms in x squared, that's 49 over 2n squared plus 63 over 2n squared. Now 49 plus 63 is 112. 112 divided by 2, that will be 56. So we have 56n squared here. And now for the terms in n, we have 49 over 6n and 63 over 2n plus 8n. So let's add the 3. So that's 49 over 6 plus 63 over 2 plus, and that's plus 8. This is giving me 143 over 3. So that means the term in n is 143 over 3n. And the answer that we now have is what we're looking for. So according to the question, they wanted us to express or to show that this summation can be expressed in the form an cubed plus bn squared plus cn, which is the same thing that we have found. So this is the answer. So let us now move to part B. On part B, they say, use the method of differences to find the summation from r is equal to 1 up to n of the form 1 over 7r plus 1 bracket 7r plus 8 in terms of n. Now, in order for us to be able to apply the method of differences, we would need, in this case, to express this fraction 1 over 7r plus 1 bracket 7r plus 8 in partial fractions. Now, I would want to assume that you already know how to express an algebraic fraction in partial fractions. So after expressing this in partial fractions, that's 1 over 7r plus 1 bracket 7r plus 8 can be expressed in partial fractions as 1 over 7 of 1 over 7r plus 1 minus 1 over 7r plus 8, like this. So this therefore means that the summation, according to what is required here in the question, the summation from r is equal to 1 up to n of 1 over 7r plus 1 bracket 7r plus 8 is the same as the summation, factoring out the 1 over 7 here, from r is equal to 1 up to n of the form 1 over 7r plus 1 minus 1 over 7r plus 8, like this. So we're going to be using the method of differences for this thing here. So we'll now be saying for the summation from r is equal to 1 up to n of 1 over 7r plus 1 minus 1 over 7r plus 8. You see how I've left the 1 over 7 for now. We're going to include it a bit later. So we just want to use the method of differences for this. We would need to know the first value, that's when r is equal to 1 for this series. So if we substitute 1 into this, we are going to get 1 over 8 minus 1 over 15. And then the second term in the series will be when r is equal to 2. And when r is equal to 2, That will be 1 over 15 minus, and r is equal to 2 here, we get 1 over 22. And for the second from last term, where r will be equal to n minus 1. Now when r is equal to n minus 1, this means that 7r plus 1 will be 7 of n minus 1 plus 1, which is 7n minus 7, plus 1, which is 7n minus 6. So when r is equal to n minus 1, this will be 1 over 7n minus 6. And that's minus 1 over 7n plus 1. And then lastly, when r is equal to n, that's the last term, we'll be having 1 over 7n plus 1 minus 1 over 7n plus 8. So these are some of the terms in the series. I've taken the first two and the last two. Okay, so I think you can notice from this series that all the terms inside of the series, like minus 1 over 15, adding to 1 over 15, and the rest in between are going to cancel out. And we are going to be left with the first term and the very last term. So it means that from the method of differences here, 1 over 7 of the summation from r is equal to 1 up to n of the form 1 over 7r plus 1 minus 1 over 7r plus 8 gives us 1 over 7 of, and we have the first term here 1 over 8, and the last term minus 1 over 7n plus 8. So this here becomes the final solution. And that's it for part B. Let us move on to part C. On part C, it goes, deduce the value of the summation from r is equal to 1 up to infinity of 1 over 7r plus 1 bracket 7r plus 8. So we've already evaluated in terms of n what we have for this summation, and we got it to be 1 over 7 of 1 over 8 minus 1 over 7n plus 8. So according to the question, they want us to find the value of the summation from r is equal to 1 up to infinity. This means that we're looking for the limit, as in this case n approaches infinity, of this expression for the summation. So we can say here this is equal to the constants. We have 1 over 7 and 1 over 8. This won't change, and that's minus. And we say as n approaches infinity, the denominator here will increase, and this means this whole fraction will approach 0. So eventually we'll be having 0 as the limit here. So here, simplifying, we just get 1 over 56, and this is the result we're looking for. And that's it for part C. And that concludes question 2. We can now move on to the next question. Question number 3. The cubic equation x cubed plus cx plus 1 is equal to 0, where c is a constant, has roots alpha, beta, and gamma. So in A, find a cubic equation whose roots are alpha cubed, beta cubed, and gamma cubed. So what we're going to do here is we're going to say let y be equal to alpha cubed, which therefore means that alpha should come out as y to the power of a third. And since alpha is a root of x cubed plus cx plus 1 is equal to 0, we can therefore substitute alpha into this. And alpha is y to the power of a third. So that will be y to the power of a third cubed plus c of y to the power of a third, that's plus 1, is equal to 0. So we can simplify this. We'll be having here y to the power of a third to the power of 3 will just give us y if we multiply the powers. And then that will be plus cy to the power of a third plus 1 is equal to 0. So we can also say here this is minus cy to the power of a third is equal to y plus 1. And if we raise both sides to the power of a third to the power of 3, then we'll be having here minus c cubed y is equal to y plus 1 cubed, which is basically y plus 1 bracket y plus 1 squared, which happens to be y squared plus 2y plus 1. So we can continue simplifying. This is going to be y multiplying the second bracket. We have y cubed plus 2y squared plus y. And 1 multiplying the second bracket. We have y squared plus 2y plus 1. That's all equal to minus c cubed y. So we have y cubed on the right side. Then 2y squared plus y squared. That's 3y squared. Then y plus 2y, that's going to be 3y. Then that's plus 1. And if we are going to take everything to one side, we'll eventually come out with y cubed plus 3y squared plus c cubed y. If I take minus c cubed y to the right side, and then we have plus 3y plus 1 is equal to 0. And finally, I can have y cubed plus 3y squared, and then that's plus, factoring out the y here, I'll be having c cubed plus 3 of y plus 1 is equal to 0. So that's the answer right here. Let's scroll down to part B. On part B, the question goes, show that alpha to the power 6 plus beta to the power 6 plus gamma to the power 6 is equal to 3 minus 2c cubed. So we're going to use the cubic equation that we got in part B, which is y cubed plus 3y squared plus c cubed plus 3 of y plus 1 is equal to 0. And we know that according to the question, the roots of this cubic polynomial are alpha cubed, beta cubed, and gamma cubed. So this is what we're going to use. Now for the summation of roots here, that's alpha cubed plus beta cubed plus gamma cubed. Summation of root for this cubic polynomial is going to be minus 3 over a. A in this case is the coefficient of y cubed. So it's minus b over a, which is minus 3 over 1. So it's minus 3. And for the sum of the product of pairs, so that will be alpha cubed beta cubed plus alpha cubed gamma cubed plus beta cubed gamma cubed. That should be d over a, which is coefficient of y in this case, over 1. So that should just give us c cubed plus 3. And then lastly, the product of the roots, that's alpha cubed beta cubed gamma cubed, should just be, in this case, minus d over a. So that's minus 1 over 1. So it should just give us 1. So we now have the sum of roots, the sum of product of pairs, and the product of roots for this cubic polynomial. Now, I would want you to keep in mind that if we have a squared plus b squared plus c squared, it can also be expressed as a plus b plus c all squared minus 2 of ab plus bc plus ac. We can apply this here now. Alpha to the 6 plus beta to the 6 plus gamma to the power 6. because alpha to the 6 is like a square of alpha cubed. So this can be compared to a squared. So this therefore should give us alpha cubed plus beta cubed plus gamma cubed squared minus 2 of alpha cubed beta cubed plus alpha cubed gamma cubed plus beta cubed gamma cubed. Now if you look here, you can see that this here is the sum of roots, which we got to be minus 3. So that's going to be minus 3 squared, and then that's minus 2 off. And if you look here, you can see that this is the sum of the product of pairs, which is c cubed plus 3. So this will give us 9 minus 2c cubed minus 6. And we know that 9 minus 6 is 3. So we have 3 minus 2c cubed. And this here becomes the answer. Let's go on to part C. On part C, they say, find the real value of C for which the matrix, and this matrix here, is singular. Now, what we know about singular matrices is that the determinant is 0. So here we're going to attempt to find the determinant of this 3 by 3 matrix. So here I'll take 1 and I'll close the row and column. So I'll be having 1 gamma cubed here, and 1. Then I'll take minus of alpha cubed and close row and column. So I'll be left with alpha cubed, gamma cubed, beta cubed, and 1. And then lastly, I'll take beta cubed, and that I'll close row and column. So I'll be having alpha cubed, 1, beta cubed, and gamma cubed. So I can now simplify this. This is 1 off 1 times 1, that's 1, minus gamma cubed times gamma cubed, that will be gamma to the power of 6. And then that's minus alpha cubed of alpha cubed times 1, that's alpha cubed, and that's minus beta cubed times gamma cubed, that should be beta cubed gamma cubed, and that's plus beta cubed of alpha cubed times beta times gamma cubed, that will be alpha cubed gamma cubed, and beta cubed times 1, that will be minus beta cubed. So let's continue simplifying. So 1 times 1, that's 1 minus gamma to the 6 minus alpha cubed times alpha cubed, that's minus alpha to the 6. Then here minus alpha cubed times minus beta cubed gamma cubed, that will be plus alpha cubed beta cubed gamma cubed, and that's plus, here we'll be having multiplying beta cubed times alpha cubed gamma cubed, we get again alpha cubed beta cubed gamma cubed, and lastly we have this times this, we get minus beta to the power of 6. Let's rearrange. So we have the 1 here, and then that's minus, and we take these terms, so that we'll be having alpha to the 6 plus beta to the 6 plus gamma to the power of 6. And then that's plus, for this 2, they're common, so that's 2 of alpha cubed beta cubed gamma cubed. Here we've got alpha to the 6 plus beta to the 6 plus gamma to the 6, and we got that to be, on part B, it gives us 3 minus 2c squared. So it's like we have right here 3 minus 2c, actually that's cubed. Okay, then that's plus 2 of, here we've got product of roots, which we got to be minus 1 here. So we put that here, so minus 1. So we simplify. This is going to give us 1 minus 3 minus 2c. So that's plus 2c cubed minus 2. And for the final answer, we have 1 minus 3, that's minus 2. And minus 2 minus 2, that's minus 4. So we have minus 4 plus 2c cubed. So this is what we now have. So we are saying that this is the determinant of the matrix, and we know that if it is singular, the determinant should be 0. So since the matrix is singular, we're going to say the minus 4 plus 2c cubed should be equal to 0. That's the determinant. So that's 2c cubed is equal to 4. So c cubed is equal to 2. So therefore c should come out as, if we cube root both sides, we get cube root of 2. So this is the final answer. And that's how we do it. Question number 4. The points A, B, and C have position vectors minus I plus j plus 2k, minus 2i minus j, and 2i plus 2k, respectively, relative to the origin or. On A, find the equation of the plane ABC, giving your answer in the form ax plus by plus cz is equal to d. So here we are considering a plane where A, B, and C are points on the plane. So in order for us to get the equation of the plane, we'll start by looking for the normal to the plane. Now for the normal to the plane, we'll first need to work out the vector AB. And for AB, we'll say that's OB minus OA, and OB is minus 2i minus j, and OA is minus I plus j plus 2k. So we can simplify this to give us minus 2i here minus j plus I minus j minus 2k, and this simplifies to minus 2i plus I, that's minus I, minus j, that's minus 2j, and that's minus 2k. So this is AB. We will also need to work out AC, and for AC we know that that's OC minus OA. So OC is 2i plus 2k, and that's minus OA, which is minus I plus j plus 2k. So that is going to give us 2i minus minus I, that's 3i, and we have here minus of j, so minus j, and 2k minus 2k, that's 0. So AC comes out as 3i minus j. So from here, we are going to use the vectors AB and AC to find the normal to the plane. So we'll do that by using the vector product. So we say the normal to the plane should be, and we have this. So that's I, j, and k. So we have for vector AB, we have minus 1, minus 2, minus 2. Then for AC, we have 3 and minus 1 and 0. So this means that the normal should come out to be, closing this, we'll be having minus 2, minus 1 and 0 for I. Then for J, that will be minus of minus 1, minus 2 and 3, 0. And that's for J. And for K, we'll be having minus 1, minus 2 and 3, minus 1 and K here. So this can be simplified to give us minus 2 times 0, that's 0, minus the product of these two, we just get minus 2i. And here we have minus 1 times 0, that's 0, minus the product of these two, that will be 6. And with the minus outside, that will be minus 6j. And lastly here, we have minus 1 times minus 1, that's 1. And that's 1 minus minus, the product of these two. And this will give us 1 plus 6, that's 7. So we'll be having plus 7k. So we now have the normal to the plane. Now for D, that will be A dot N. A is any point on the plane. So we can take any point on the plane. Let's take the point A, that's minus 1. That's minus I plus j plus 2k. So that'll just be, I'll write it in this form, in column vector form. And that'll be minus 1, 1, 2. And we also have the normal in column vector form, that will be minus 2, minus 6 and 7. So if we do the dot product here, we'll get minus 1 times minus 2. So that's 2. And 1 times minus 6, that's minus 6. And 2 times 7, that's 14. And this gives us 10. So eventually we will say the equation of the plane will come out as r dot, the normal, which is minus 2i minus 6j plus 7k is equal to d, which is 10. Okay, and if we want to write it in Cartesian form, that will be minus 2x minus 6y plus 7z is equal to 10. So this here is the answer. That's what we get. So for part B, find the perpendicular distance from O to the plane ABC. Now, to find the distance from the origin to the plane, we're going to say d over modulus of n. Now, we had gotten d to be, in this case, we got it as 10. So we have 10 here. And it's divided by the modulus of n, that's the normal. So it'll be the square root of, and the normal, we'd gotten it to be minus 2i minus 6j plus 7k. So this is going to be minus 2 squared plus minus 6 squared plus 7 squared. So this is what we have. So we can just simplify this, and it's going to give us 10 over, then the square root of 4 plus 36 plus 49. And this gives us 89. So that will be square root of 89 down there. So this is the perpendicular distance from the origin to the plane. And lastly, let's look at part C. For part C, it says find the acute angle between the planes OAB and ABC. Now, to find the acute angle between two planes, we would need to know what the normals to the planes are. And we're going to say the normal to the first plane dot the normal to the second plane is going to be equal to the modulus of the first plane plus the modulus of the second vector of the plane multiplied by cosine of theta. So the normal to the plane ABC, we have it already, but would want to find the normal to the plane OAB. So let's call the normal to the plane OAB N1. So for N1, we are going to use the vector product, and we have I, J, and K here. Now we would need two vectors that are on the plane, and since it's a plane OAB, we can just find OA and OB. So for OA and OB, we have the vectors for OA, that will be minus I plus j plus 2k. So the scalars will be minus 1, 1, and 2. So we have right here minus 1, 1, and 2. Then for or B, we'll be having minus 2 and minus 1. So we have right here minus 2 and minus 1. So this will be 0. So this will simplify to 1, 2, minus 1, 0, I, minus 1, 2, minus 2, 0, J, and that's plus minus 1, 1, minus 2, minus 1, and that's of K. So this simplifies to, for this one, we can be having 2I, and that's minus, this gives us minus 4J, and here we should get 3K. So we now have the normal to the plane or AB. So with this normal, we're going to say the dot product for the two normals. So we take the scalar for n1, that's 2 minus 4, 3, and this dot times the normal to the plane ABC. Now the normal to the plane ABC, we got it to be minus 2I minus 6J plus 7K. So that's minus 2, minus 6, 7. So it's dot minus 2, minus 6, and 7. And this is going to be equal to the modulus of n1. So that's going to be square root of this one, which is 2 squared plus 4 squared plus 3 squared times the modulus of the other vector. That's going to be 2 squared plus 6 squared plus 7 squared, and is cosine of theta. So let's simplify this. So here we'll be having 2 times minus 2, that's minus 4, and that's plus 24, and that's plus 21, is equal to, here 4 plus 16 plus 9, we get 29, and here 4 plus 36 plus 49, we get 89, and that's cosine of theta. Okay, and minus 4 plus 24 is 20, 20 plus 21, that's 41. So eventually we have cosine of theta coming out as 41 over the square root of 29 times the square root of 89. So we'll be having theta is equal to, and we use the calculator, so that will be shift cos of 41 over root 29 times root of 89, and this gives us 36.2 degrees. So that's 36.2 degrees, and that's the answer right here. Question number 5. Prove by mathematical induction that for every positive integer n, d to the 2n minus 1 over dx to the 2n minus 1 of x sine x is equal to minus 1 to the power n to the negative 1 of x cos x plus 2n minus 1 sine x. So this is mathematical induction. So here we're going to start to prove for n is equal to 1. And for n is equal to 1, I'll take the left hand side. And for the left hand side, if I substitute 1 on 2n minus 1, that will give me 1. So that will just be d by dx of x sine x. Now differentiating x sine x gives us sine x plus x cos x. And then let's go to the right hand side. For the right hand side, we have substituting 1 for n. That will just be minus 1 to the power of 1 minus 1. That will be 0. And that's x cos x. And 2n minus 1 is 1. So that will be plus sine x here. So it just gives us here Minus 1 to the power 0 is 1, so we have x cos x plus sine x. Now you can notice that the left hand side is coming out to be equal to the right hand side when n is equal to 1. Hence, it's been proved true for n is equal to 1. So that's it for n is equal to 1. Let's move on to the assumption. So we assume true for n is equal to k. So what does that mean? It means we're substituting k for n in this formula. So that will be d to the power 2k minus 1 over dx to the 2k minus 1 of x sine x being equal to minus 1 to the k minus 1 of x cos x plus 2k minus 1 sine x. So we now have this formula here. Now from here, we're now going to get to prove for n is equal to k plus 1. Now if n is equal to k plus 1, it means that we're going to be substituting k plus 1 in place of n. Now where we have 2n minus 1, it will now be 2 of k plus 1 minus 1, which is 2k plus 2 minus 1, which is like 2k plus 1. So this means that we'll now be having d to the 2k plus 1 over dx to the 2k plus 1 of x sine x. So here, you need to understand that what we have right here now is the same as saying d by dx of d to the 2k over dx to the 2k of x sine x. Which means that to simplify this, we are going to need to find first d to the 2k of dx to the 2k of x sine x. And how can we find it? If you look at the assumption that we have here, we have it in the form d to the 2k minus 1 by dx to the 2k minus 1. So if we would want d to the 2k, we can differentiate the assumption, which is d to the 2k minus 1 over dx to the 2k minus 1 of x sine x, like this. So now, let's simplify this. This is the same as saying d by dx of, and d to the 2k minus 1 by dx squared dx to the 2k minus 1 of x sine x. We have it from the assumption as minus 1 to the k minus 1 of x cos x plus 2k minus 1 sine x. So this is what we have here. So let's simplify this. So we now have here minus 1 to the k minus 1 of, and we differentiate x cos x. We get cos x minus x sine x. And differentiating 2k minus 1 of sine x, we get 2k minus 1 of cos x. So this is what we now have. Now we can simplify a bit more. So we have minus 1 to the k minus 1 of, and here we've got minus x sine x, and for the like terms we have cos x plus 2k minus 1 of cos x. So if we factor out cos x, we'll be having 1 plus 2k minus 1 So that will just give us 2k cos x. So we now have this for d to the 2k by dx to the 2k of x sine x. So we are now going to use this for our expression when n is equal to k plus 1. We say that this is going to be equal to d by dx of d to the 2k by dx to the 2k of x sine x. And this is what we have obtained here. So we're now saying this is going to give us d to the 2k plus 1 over dx to the 2k plus 1 of x sine x will be equal to d by dx of d to the 2k by dx to the 2k of x sine x, which is the one that we got here. So that will be d by dx of minus 1 to the k minus 1 of minus x sine x plus 2k cos x. So let's now simplify this. So we now have here differentiating, we have minus 1 to the k minus 1, and here differentiating minus x sine x, we get minus sine x minus x cos x. And differentiating here 2k cos x, we get minus 2k sine x. And we can simplify this a bit further. So that's here minus x cos x. And for the like terms, we have minus sine x and minus 2k sine x. So this is the same as minus of 2k plus 1 of sine x, like this. Now we can factor out the negative sign. So that will be minus 1 to the k minus 1, and factoring out minus 1. And inside the bracket, we'll now be having x cos x plus 2k plus 1 sine x. Now multiplying minus 1 to the k minus 1 times minus 1 here, which is a power 1, we can add the powers to get minus 1 to the k of x cos x plus 2k plus 1 sine x. And what we have here is the proof. Now, how is it the proof, you may ask? Okay, let me take you back to the original formula. And let's put it here. Now remember, here we wanted to prove for n is equal to k plus 1. Now, from the original formula, the power to minus 1 is n minus 1. So putting k plus 1 there, that would be k plus 1 minus 1. So in our proof, that should come out to be just k. And we have the k here. And here, multiplying sine x, we had 2n minus 1. So substituting k plus 1 there, that should have been 2 of k plus 1 minus 1, which is 2k plus 2 minus 1, which is 2k plus 1. And that's what we have here, 2k plus 1. So this is showing us that this here is the proof that the formula is true for n is equal to k plus 1. So we will write the concluding statement. So it is also true for n is equal to k plus 1. Hence, by mathematical induction, it is true for all positive integers. And that's the concluding statement, and that's how we work out this problem here. Question number 6. The curve C has equation y is equal to x squared plus x minus 1, all divided by x minus 1. So on A, find the equations of the asymptotes of C. So right here, we're going to start with the vertical asymptote. And for the vertical asymptote, we're just going to say here, the denominator, x minus 1, we equate it to 0. So the vertical asymptote should just come out as x is equal to 1. So that's the vertical asymptote here. And if you look here, you can see that the degree of the numerator is 1 greater than the degree of the denominator. This means that we have an oblique asymptote. So let's talk about the oblique asymptote. And to find it, what I'll do is I'll divide x minus 1 into x squared plus x minus 1. So x squared plus x minus 1 here. So x into x squared, that's x, and x multiplying x minus 1, we get x squared minus x. So I'll subtract here, and x squared minus x squared, that's 0, and x minus minus x, that's 2x here. Bring down the minus 1. X into 2x, that's plus 2, and multiplying 2 times x minus 1, we get 2x minus 2, and subtracting, the remainder here comes out as minus 1 minus minus 2, so the remainder comes out as 1. But what we're concerned about is the quotient here, which is x plus 2, and therefore the equation of the oblique asymptote will come out as y is equal to x plus 2. So this is what we have for the oblique asymptote. So these are the equations of the two asymptotes of the curve C. Part B. Show that there is no point on C for which 1 is less than y is less than 5. So let's take the original equation and let's place it here. So from this equation, I'm going to multiply both sides by x minus 1. This means that we'll be having y of x minus 1 is equal to x squared plus x minus 1. So I'm going to express this as a quadratic in terms of x and y. That's the aim. So this means that we'll be now having xy minus y, and that's equal to x squared plus x minus 1. So I'll take everything to one side. So that should mean that I'll take xy minus y to the other side. So we'll be having here x squared plus x, and that's minus xy, and minus y becomes plus y, and we have the minus 1 here, and that's all equal to 0. And we can simplify this a bit to x squared plus, and here we have x common, so that will be 1 minus y of x, and that's plus y minus 1 is equal to 0. Now, since according to the question, they want us to show that there is no point on C for which y takes these values, it also means that there are no values of x for which these values exist. And this means to us that b squared minus 4ac should come out less than 0. So in this case here, a is the coefficient of x squared, that's 1, b is 1 minus y, and c is y minus 1. So if we do the discriminant, we'll be saying 1 minus y squared minus 4 of 1 of y minus 1 should be less than 0. Expanding, this is going to be 1 minus 2y plus y squared, that's minus 4y plus 4 is less than 0. And this simplifies to y squared minus 6y plus 5 is less than 0. And here we can also factorize. So this is y here and this is y here. And factors of 5 whose sum is minus 6, we have minus 5 and minus 1. So we have two critical points here, and the critical points are 1 and 5. So what we're going to do here is we'll just have a small sketch of the quadratic graph, and we have y here, and it's a U-shaped parabola with the critical values here being 1 and 5, plus, minus, plus. So the graph is less than 0, that is negative, for values of y between 1 and 5, that's where it's below the y-axis. So therefore we can conclude that 1 is less than y and is less than 5. That's the range of values that satisfy this inequality. And that's actually the proof. That's how we show that there is no point for which y ranges between these two values. And that's the answer that right there to part B. So let's move on to part C. It says find the coordinates of the intersections of C with the axis and sketch C. So we're going to start with the intersections. Let's start with the y-intercept. Now the y-intercept occurs when x is equal to 0. Now we have the equation here of the curve C. So we're saying when x is equal to 0, you can see that y will be minus 1 over minus 1. So y is equal to 1. Therefore, the y-intercept is coordinate 0, 1. And let's now look for the x-intercepts. For the x-intercepts, we know that y is equal to 0. So if y is equal to 0, this means that we'll be having 0 is equal to this, and we multiply both sides by x minus 1. So we'll be having something like x squared plus x minus 1 is equal to 0. Now we can solve this for x, and I'm going to use the calculator for convenience. So I'll go to equation, that's 5, and quadratic, that's option 3. And to solve this, the coefficients a, b, and c are 1, 1, and minus 1. So we have 1, 1, and minus 1. So we have it like this. So we can now have the first value as minus 1 plus root 5 all over 2. So x is equal to minus 1 plus root 5 all over 2. And the other value, we can also get it from the calculator as minus 1 minus root 5 over 2. So minus 1 minus root 5 over 2. So the coordinates for the x-intercepts, that's the intersection of the curve with the x-axis, will be minus 1 plus root 5 over 2, 0, and minus 1 minus root 5 over 2 and 0. So these are the other two intercepts or intersections of the curve with the axis. Now they also say sketch C. So we now want to make a sketch of the curve. So I'll have the two axes, and with the two axes we have the y-axis here and the x-axis here and the origin here. I'll start with the asymptotes. Now the asymptotes, we have a vertical asymptote of x is equal to 1 and an oblique asymptote of y is equal to x plus 2. So let's make use of that. So let's start with x is equal to 1. That's the vertical asymptote. So it crosses the x-axis at 1. And then for the oblique asymptote, it's y is equal to x plus 2. So it's a line perhaps like this. So this here is the oblique asymptote crossing the x-axis at minus 2 and the y-axis at 2. So this is what we have right here. So for the graph, we'll be having it like this here, and also here it'll come all the way like this. It doesn't touch the asymptotes, so kind of like this. So this here is the graph for the curve C. Let's move on to part D. On D, they say sketch the curve with the equation y is equal to modulus of x squared plus x minus 1 over x minus 1. So this is a modulus graph, and we know that the modulus graph is simply reflecting the original graph in the positive x-axis. So what I'm going to do here is I'll reflect the part of the graph that is below the x-axis above the x-axis. So I'm just going to take here just this part, because this part will remain, and place it here. So this is the part of the graph that is above the x-axis, so it'll remain. And the part that is below the graph is going to be reflected above the graph. So it means that this tail here is going to be reflected upward. So we'll be having it like this. And also here, we have this part of the graph from here going all the way down. I'll reflect it up here. So I'll have it like this. Okay, let me try again. So it'll come like this, and here. So this is more like the graph, and that's how we do it. And that's it for part D. Let's move on to question number 7. Question number 7. Show that the curve with Cartesian equation x squared plus y squared to the power of 5 over 2 is equal to 4xy bracket x squared minus y squared has polar equation r is equal to sine 4 theta. Now to simplify this, we are going to use these important results. So that means that for x squared plus y squared, we are going to use r squared, and that's to the power of 5 over 2, and that's equal to 4xy, so that's 4, and in place of x, we have r cos theta, and in place of y, we have r sine theta, and that's multiplying x squared, which is r squared cos squared theta, minus y squared, which is minus r squared sine squared theta. So we can now simplify this. So here, I'll take the 4, and r times r is r squared, and I'll also take out the r squared, factoring it out from here. So that means I'll be having 4r to the power of 4. And here we'll be having sine theta cos theta. And inside the bracket, we're left with cos squared theta minus sine squared theta. Now here, I would want to apply a double angle identity. So I'll express this here as 2r to the power of 4 of 2 sine theta cos theta bracket cos squared theta minus sine squared theta. Okay, because for the double angle identity, 2 sine theta cos theta is actually sine 2 theta, and cos squared theta minus sine squared theta from the double angle trig identity will be having cos 2 theta. So this is what we now have. But again, we can still apply the double angle formula for 2 sine 2 theta cos 2 theta and it is going to give us sine 4 theta. So we now have it like this. So all this is equal to r squared to the power of 5 over 2. And multiplying the powers, this gives us r to the power of 5 throughout. So if we divide both sides by r to the power of 4, then it means r comes out as sine 4 theta. And that's what we get right here, hence shown. Let's move on to part B. It says, the curve C has polar equation r is equal to sine 4 theta for values of theta between 0 and a quarter pi. Sketch C and state the equation of the line of symmetry. Now we want to make a sketch of the graph r is equal to sine 4 theta. And to do that, I'm going to start with the Cartesian graph of r is equal to sine 4 theta. So for the Cartesian graph, I'll have 0 here, and r here, and theta here. And I'm going to let 4 theta be equal to pi over 2, which means theta is equal to pi over 8. Which means that on this Cartesian graph, I'll have pi over 8 increments throughout. So this is going to be pi over 8. And this here is going to be 2 of pi over 8, which is pi over 4. So since our graph is going to range from 0 to pi over 4, there's no need for me to continue adding the increments. So let's just have a sketch from 0 to pi over 4. Now we're saying when theta is equal to 0, what is r? So when theta is equal to 0, that will be 4 of 0. So that's sine of 0, and sine of 0 is 0. So we'll be having a point here. And when theta is equal to pi over 8, r will be equal to sine of 4 of pi over 8, which is sine of pi over 2, which is basically 1. So we know that r is equal to 1 when theta is equal to pi over 8. So we can have 1 around here. So pi over 8 corresponds to 1. And then when theta is equal to pi over 4, it means that we'll be having r is equal to sine of 4 of pi over 4, which is sine of pi, which is 0. So it means that at pi over 4, r is 0. So we can have our sketch like this. Not perfect, but that's basically the Cartesian graph for r is equal to sine 4 theta. So we're going to translate this now to the polar graph. So we have our two axes, and here we've got the initial line theta is equal to 0, and here we've got pi over 2, and this is here the pole. And now we are going to have pi over 8 and pi over 4. Now pi over 4 is halfway through, so it could be somewhere here. So this is pi over 4, and we also have pi over 8, which should be somewhere around here. So this is pi over 8. And for our graph, you can see that from theta is equal to 0, it is increasing as it approaches r is equal to 1. So we can translate this to the graph coming from 0 and approaching an r value of 1. And now as it approaches pi over 4, r is decreasing all the way down to 0. So it means the graph will then come back again, approaching pi over 4 as it goes back to 0. So like this. So this is how we get the graph for r is equal to sine 4 theta. And that also say that we need to state the equation of the line of symmetry. So line of symmetry is the line here. That's theta is equal to pi over 8. That's the line of symmetry right here. Let's go to part C. Find the exact value of the area of the region enclosed by C. Now, in order for us to find the enclosed area, we know that we use the formula area is equal to the integral from alpha to beta of half r squared d theta. So this is what the formula that we're going to use here. And the equation is r is equal to sine 4 theta, and the limits are 0 and a quarter pi. So we'll be saying here the area in this case is equal to the integral from 0 to a quarter pi of half of r squared, and since r is sine 4 theta, that will be sine squared 4 theta, and that's d theta. Now we're going to use the identity sine squared a is equal to half of 1 minus cos 2a, which means that we'll be having 0 up to a quarter pi. I'll factor out the half outside. So for sine squared 4 theta, that is going to give us half of 1 minus cos of, in this case, 8 theta d theta. So let's integrate this. Now half and a half give us a quarter, and integrating 1 we get theta, and integrating cos 8 theta we get 1 over 8 sine of 8 theta, and that's from 0 to a quarter pi. So we can simplify this. So we have a quarter here, and substituting a quarter pi into this, we have a quarter pi, and that's minus. Substituting a quarter pi for theta here, that's 8 times a quarter pi, that gives us 2 pi. So sine of 2 pi is 0, so we just get 0 here. And substituting 0 into this whole thing again gives us 0. So basically we'll be having a quarter times a quarter pi, which gives us 1 over 16 pi. And this is the answer right here, enclosed by C. Let's scroll down to the last question. Part D. Using the identity sine 4 theta is identical to 4 sine theta cos cube theta minus 4 sine cube theta cos theta. Find the maximum distance of C from the line theta is equal to a half pi, giving your answer correct to 2 decimal places. Now here they want us to find the maximum distance of the curve C from the line theta is equal to half pi. And if we go back to the graph, the line theta is equal to pi over 2 is this vertical line. So we want to find the maximum distance from this line to the curve. This means that we are looking for the maximum x distance from this vertical line to the curve. So in order for us to be able to do that, we will need the x equation of the polar curve. And we know that x is equal to r cos theta. And in our case here, the equation of the curve is r is equal to sine of 4 theta. So we can therefore say that the x equation for this graph will be x is equal to r, which is sine 4 theta, multiplying cos theta. Now we are supposed to use the identity, which is the one given here. So in place of sine 4 theta, I'll put this expression here. So I'll be having cos theta multiplying 4 sine theta cos cubed theta minus 4 sine cubed theta cos theta. And I can just simplify this, multiplying cos theta by the terms in the bracket. That'll be 4 sine theta and cos to the 4 of theta minus, and here I'll be having 4 sine cubed theta cos squared theta. Now, we know that for the maximum distance, here, dx by d theta should be equal to 0. So let us find, in this case, dx by d theta. Let's differentiate x with respect to theta. Alright. Let's start with 4 sine theta cos to the 4 of theta. We're going to use the product rule for differentiation. So that means we'll be saying cos to the 4 of theta times the derivative of 4 sine theta plus 4 sine theta times, here it says it has to be d theta, so yeah, d by d theta of cos to the 4 of theta, and that's minus, open bracket. We do the product rule here for this, so it's cos squared theta and d by d theta of 4 sine cubed theta, and that's going to be plus, and we be having 4 sine cubed theta and d by d theta of cos squared theta. So we can continue simplifying. So for this one, we have cos to the 4 of theta, and differentiating with respect to theta, 4 sine theta, we get 4 cos theta, and that's plus, coming here, we have 4 sine theta, multiplying the derivative for cos to the 4 of theta, and that'll be 4, rather, that'll be minus 4 cos cubed theta sine theta, and that's minus, I'll have some space down here, minus, and for here we'll be having cos squared theta, and differentiating 4 sine cubed theta, we get, bring down the 3, that'll be 12 sine squared theta cos theta, and then that's plus, here we have 4 sine cubed theta, and differentiating cos squared theta, we'll be having 2 cos theta sine theta. So let's simplify this a little bit more. So cos to the 4 of theta dot 4 times 4 cos theta, we get 4 cos to the power 5 of theta. And then here, 4 sine theta times minus 4 cos cubed theta sine theta, that will give us minus, and we'll be having 16, and cos to the 3 of theta, and sine squared theta. And coming here, we'll be having minus 12, and that'll be sine squared theta and cos cubed theta. And the last one here, that'll be plus, and we have 4 times 2, that's 8, and that'll be cos theta, and we'll be having sine to the 4 of theta. So with what we have right here, I'm going to factor out cos theta, which is common throughout. So this will give me factoring out, rather let me factor out 4 cos theta. So factoring out 4 cos theta, I'll be having inside the bracket, here we'll be having cos, to the 4 of theta, and here we'll be having, that will be minus 4 cos squared theta sine squared theta, and here we'll be factoring out again. We'll get minus 3 sine squared theta cos squared theta, and lastly here we'll be having 2 sine to the 4 of theta. So this is what we now have. Now we can again simplify. We have 4 cos theta, so that's cos to the 4 of theta, and this 2 here I like, so we can add the 2 to get minus 7 cos squared theta sine squared theta, and then that's plus 2 sine to the 4 of theta. So this whole thing here is supposed to be equal to 0, since we said dx by d theta for the maximum distance should be equal to 0. So we should equate this thing here to 0. So therefore 4 cos theta bracket cos to the 4 of theta minus 7 cos squared theta sine squared theta plus 2 sine to the 4 of theta should be equal to 0, which means either 4 cos theta should be equal to 0, or this cos to the 4 of theta minus 7 cos squared theta sine squared theta plus 2 sine to the 4 of theta is equal to 0. So here I'll divide all the terms by cos to the 4 of theta. So cos to the 4 of theta here by cos to the 4 of theta, here by cos to the 4 of theta, and here by cos to the 4 of theta. So cancelling out here, we get 1, and here cos squared theta gets into, and here we'll be having squared and sine squared theta over cos to the 4 theta. That gives us tan squared theta. So we'll be having minus 7 tan squared theta here. And here sine to the 4 theta over cos to the 4 theta gives us tan to the 4 of theta. That will be plus 2 tan to the 4 of theta, and that's equal to here 0. So we can just rearrange this to 2 tan to the 4 of theta minus 7 tan squared theta plus 1 is equal to 0. So let's solve for tan theta. Here it's more like a disguised quadratic, so we can say let y be equal to tan squared theta, which means the equation will now come out to be 2y squared minus 7y squared plus 1 is equal to 0. So we can solve this with the calculator. Okay, so let's take the calculator here and we put it in equation mode. So that's option 5, and quadratic, that's option 3. So we have 2 here, so 2, and here minus 7, so minus 7, and 1, so again we store 1, and then the first result will come out as 7 plus root 41 over 4. So y is equal to 7 plus root 41 over 4, or the other value should be 7 minus root 41 over 4. So 7 minus root 41 over 4. But we know here that tan squared theta is equal to y. So therefore tan squared theta can be equal to 7 plus root 41 over 4, or tan squared theta can also be equal to 7 minus root 41 over 4. Now let's have this in decimal form. So we have here the 7 plus root 41 over 4, and this is 3.351. So tan squared theta here is 3.351, and we can do the square root to get tan theta here. So tan theta will be the square root of this. So we just say square root, and we get 1.831. So 1.831, and that's going to be plus or minus here. And for tan squared theta is equal to 7 minus root 41 over 4. Let's type that in. So we're saying 7 minus root 41, 7 minus root 41 divided by 4, and this gives us 0.1492. So 0.1492, so that's tan squared theta. Therefore tan theta will be the square root of this. So square root, and we get 0.386. So 0.386, and it has to be plus or minus. So 0.386 plus or minus. Okay, so to get theta, we're going to say theta is equal to, in this case, arctan of 1.831. So that's second function tan. Let's bring it here, of 1.831, and we're in radians, so that's 1.071. So plus or minus 1.071. So that's what we have for theta here. And here theta will be arctan of 0.386, and using the calculator, that's second function tan of 0.386, and this gives us and that's 0.368. So we have 0.368 here, and plus or minus. Now if you substitute these values into x, remember we'd gotten x to be equal to r cos theta, and x is here sine 4 theta dot cos theta. That's a simpler one. So sine 4 theta cos theta. So if we are going to substitute these values of theta into this, you're going to find that we will get maximum value of x when theta has the value 0.368. So when theta has this value, it means x is equal to, and let's type that in, that's sine of 4 times 0.368 cos of theta, that's 0.368, and we get 0.9284. That's 0.928. So x has a value of 0.928. So this here will be the maximum value of x. And that's how we work out this problem here. And that concludes again this paper.